Well, good afternoon, everybody. Welcome back to Intro to Physics, day 17. I did count yesterday. This is day 17. And we are going to continue the lesson that we started yesterday on energy and kinetic energy, work, that sort of thing. And then carry that on over into power and gravitational potential energy and start talking about those other forms and how energy is conserved within a system. So let me share my screen with you guys and we will get started. All right. So can you guys all see this example that we worked on yesterday? Part A?
Yes.
Perfect. So just a quick recap. We did part A together. And the purpose of part A was to find the speed of the hammerhead just as it hits the I-beam. So this hammerhead is raised up and allowed to fall back down. And as it falls, it hits this beam, which is then driven down into the ground. So yesterday, our goal was to try to find how fast it was moving right when it hit the beam, taking into account the fact that there's friction between the hammerhead and the rails, and that it is dropping from rest at the top. And this time, instead of using our projectile motion type equations, we're using our work equations and energy. And so you'll find as you go throughout physics that some of these topics kind of combine with each other, and you'll find that there's more than one way to solve a certain problem. So it's a good idea to not just forget everything as soon as you've moved on from it, because all of these ideas do build on themselves. And yeah, you can use like kinematic equations for a problem or momentum or energy. It just depends on what you're given and what makes the most sense to do. Anywho, I wanted to move into part B of this example with you today. So let's do that. So part B asks to find the average force that the hammerhead exerts on the I-beam. Right, so now we're thinking after it has already fallen, it is contacting the I-beam, how much force is it exerting on that I-beam? So now we're thinking about this distance here between point 2 and point 3. So the hammerhead has already fallen down from point 1. Remember, point 2 is right at the top of the I-beam, and point 3 is after it's been driven down that 7.4 centimeters. I know we had the question at the end of yesterday, like, why do we even need that number? We're going to use that number today, right? That's the displacement from point 2 to point 3. So in this portion of its motion, remember, we're going to be looking at this free body diagram over here, this part C, figure C, free body diagram. Because now not only do we have the weight or the force of gravity pulling the hammerhead down, we also have the force of friction opposing that motion, so up the rails. And since the hammerhead is now contacting the I-beam, we have that normal force, that supporting force from the I-beam kind of holding up the hammerhead as it hits. So now we have 3 forces that we're dealing with instead of just 2 like we did when it was falling. So that means that the sum of our forces in the y direction, or vertically, all of the forces, when we take them into account with their direction, we have the normal force pointing up because it's supporting the hammerhead going up. We have the friction force pointing up because it's opposing the motion down. And then we have the weight downward towards the center of the earth. So that is a negative force because my convention is that up is positive and down is negative. So that's the sum of our forces in this free body diagram. That means that the total work that is done during this little displacement is the sum of the forces times the displacement. So we found yesterday in part A that the initial, well, in that case, it was the final kinetic energy, but the kinetic energy at point 2, K2, is 5,700 joules. So now, since we're starting at point 2, that's why I'm calling it our initial kinetic energy at this point of the problem. After this hammerhead drives the I-beam into the ground, it can only drive it so far and then it will stop moving. So it'll only drive it 7.4 centimeters and then it will stop. So that means the final kinetic energy or the kinetic energy after it's driven in 7.4 centimeters is 0 joules because it is no longer moving. Remember, kinetic energy is energy of motion. So we only have a positive kinetic energy if the object is moving. And at this point, it's no longer doing that. So we have a final kinetic energy of 0. Okay. We learned yesterday about the relationship between work and energy in the work energy theorem. So that told us that the total amount of work done on an object is equal to the change in the kinetic energy. So if the total work is the sum of the forces times displacement, and that is also equal to the change in kinetic energy, then we can write our equation as such here. Okay, so we want to find the average force the hammerhead exerts on the I-beam. So we're asking for that normal force, that contact force between the two objects. That's the normal force. So if we take our equation here and we rearrange it using algebra to solve for the normal force. I didn't write out all the steps just because there wasn't a whole lot of space here on this slide, but I'll talk through them. What we do is we divide both sides of the equation by d23. Remember, that's the displacement from point 2 to point 3. So we divide both sides by that d23. And then we subtract the friction force and we add the weight on both sides. So we end up with the normal force being equal to the weight minus friction minus K3 minus K2 over the displacement. So that change in kinetic energy over the displacement. All right, we found yesterday in part A, the weight of the hammerhead, which was mass times G, so 200 kilograms times 9.8 gave us this weight of 1960 newtons. We know that the friction force is 60 newtons because that's given to us in the problem statement. The final kinetic energy is 0, again, because it's no longer moving after that. The kinetic energy at point 2, we found in part A to be 5,700 joules. And then the displacement from point 2 to point 3 is that 7.4 centimeters. We have to convert those units, though, to meters in order to keep it consistent with joules, because remember, joules is newtons times meters. So in order for our meters and the joules to cancel out with the meters of the displacement, they need to be the same unit. So once we do all of that math, we find that a normal force of 79,000 newtons, which is quite a bit of force. Okay, do you guys have any questions about this example? Part A or part B?
The normal force and average force the same thing?
For this purpose, yes. In general, you may not want to make that assumption, but since we're talking about the force that the hammerhead exerts on the I-beam, we're talking specifically about that contact force. And so in this case, we're thinking about it like, so an average force would take into account the amount of force over that whole like time interval, right? So over that whole time interval that this is being displaced, that would be our average force, or in this case, it would be our normal force.
Okay.
Any other questions? Okie dokie. Well, here is another problem that I want you to give a try yourself. Just try to set it up, think through it, take a minute. I'll read it to you guys, but then I want you to think through how you might go about trying to answer this question. 2 ice boats hold a race on a frictionless horizontal lake. The 2 ice boats have masses m and 2m. Each ice boat has an identical sail, so the wind exerts the same constant force F on each ice boat. The two ice boats start from rest and cross the finish line a distance S away. Which ice boat crosses the finish line with a greater kinetic energy? Okay, so I want you to take just a minute and think about it. Try to come up with an answer, and then we'll talk through it together in just a minute. All right, so let's think through this. And even if you don't quite remember like the exact equation for kinetic energy that we talked about yesterday, you want to try to remember what kinetic energy depends on. So it depends on the mass of the object that you're trying to move and how fast you're moving it. Now, it depends more so on how fast you're moving it, right? Because the equation is 1/2 mv squared. So that speed is important, but the mass is also important. Okay. Also, just try to think about this in terms of like your everyday experience, maybe. So, like pushing a shopping cart, for example. If you have a shopping cart that's got like a little bit of stuff in it, it's fairly easy to push. It's fairly easy for it to start moving fast. But if it has twice as much stuff in it, it's going to take a bigger force to make it move fast. Or if you're pushing it with the same amount of force, that just means it's going to be moving a lot slower. So even though this blue boat is much more massive, is twice as massive as the red boat, it's also going to be moving a lot slower. Okay, so the kinetic energy is the total work done to accelerate it from rest, right? Both of these boats are starting from rest. They are not moving at the beginning. We know that work is force times the displacement. Both of these boats are traveling the same distance, so they have the same displacement. They both have the same horizontal force acting on them. So they have the same kinetic energy. But one of them is going to get there first, right? The red boat gets there first because it can move faster. But that wasn't the question. The question was, which one has the greater kinetic energy? They are equal amount of kinetic energy, but the red boat will win. Okay. So moving on into a related topic, power. You might have noticed from our equation for work that it doesn't directly depend on time, right? It depends on force, displacement, and the angle between the two of those. But you don't find time in that equation. So if we're lifting a barbell that's 100 newtons through a distance of 1 meter at a constant velocity, we do 100 joules of work, no matter how long it takes us to do that, right? The force times the displacement. So 100 newtons times 1 meter gives us 100 joules of work. It doesn't matter how fast you do that, it's the same amount of work. However, if you exercise a lot, if you lift things in your life, you know that the amount of time it takes you to do something does actually kind of factor into your workout, right? So often we need to know how quickly that work is done, and that's this word power. Okay, so power takes into account the time, whereas work does not. Work just depends on the force, the displacement, and the angle between the two. Okay, so power is really our a new idea. So the symbol for power is capital P. Lowercase p, which we'll see next week, is momentum. The unit of power is watts, which unfortunately is a capital W, just like our symbol for work. And now work is incorporated into the equation for power. So don't be confused by the super confusing thing. So 1 watt is 1 joule per second. We can also measure power in horsepowers. So 1 horsepower is 746 watts. And power is also a scalar because work is a scalar and time is a scalar. So the average power, here's our equation, and it's actually kind of a list of equations because there are multiple ways to calculate this. Right, so our average power is how quickly work is done. So the amount of work over a time interval. So W, work over our change in time. We also know, though, from the work energy theorem that work is the change in kinetic energy. So we have change in energy over change in time. We also know that work is the force that acts in the direction of motion. So those two lines, remember, means parallel. So the force that's parallel to the motion or in the direction of the motion times our change in distance or times our displacement, right? Work is force times displacement. And then again, power would be divided by that time interval. But we also should remember from the second week of class, maybe, that our change in distance over change in time is how we calculated average velocity. So power is also that parallel force times our average velocity. Whew, lots of ways to calculate it. Instantaneous power, very similar to the difference between like average velocity versus instantaneous velocity, is instantaneous power is the limit as that time interval gets smaller and smaller and smaller. Okay, so this would be where a derivative comes into play if it is needed. And so you can see here we end up with a dot product as well, because that dot product tells us how much of the force is parallel to the motion or in the same direction of the motion. Okay, so here are quite a few equations for power. And again, which one you use kind of depends on what you're given in this scenario. So my recommendation is to write down all of them. But if you want to save space in your equation sheet, then just remember that power is how fast we do the work, how quickly work is done, work divided by our time. And from that, we can kind of derive the other ones. Okay, so here's an example. Example 4. Each of the 2 jet engines in a Boeing 767 airliner develops a thrust or a forward force of 197,000 newtons. When the airplane is flying at 250 meters per second, what horsepower does each engine develop? Okay. So thrust, that force is forward. It's in the direction that the airplane is moving. So our parallel force is equal to the thrust. All of that force from the thrust is in the direction of motion, right? So all of that number is going towards helping the airplane move, right? All of that is important. We don't have an angle that we're considering. So that means based on what we're given, the best version to use of that power equation is the parallel force times the velocity or times the speed. Right, so we have, and I went ahead and wrote it in scientific notation just to practice that skill again. 197,000 newtons is the same thing as 1.97 times 10 to the 5 newtons. That's our parallel force. And then the speed is 250 meters per second. So we end up with a power of 4.93 times 10 to the 7 watts. We wanted that number to be in horsepower though, or the question did. So we're going to use that conversion factor that I listed on the previous slide. 1 horsepower equals 746 watts. And again, this is just a chance for us to practice that skill of unit conversion. So remember, I like to set them up as ratios or as fractions so that we can see this unit watts on top cancels out the watts on the bottom. And we're left with our unit of horsepower, which is the one that we want. So we'd multiply the numbers on top, divide by the numbers on the bottom. So 4.93 times 10 to the 7 times 1, divided by 1, divided by 746 gives us 66,000 horsepower. So I have a fun fact here. I don't know how many of you guys are like aerospace people or interested in airplanes, but I have this fun fact written down that I want to share with you. So the largest propeller-driven airliners of the 1950s had engines that developed about 3,400 horsepower, which gave them max speeds of 600 kilometers per hour or 370 miles per hour. And so each engine in a Boeing 767 develops nearly 20 times more power. So they can fly at about 900 kilometers per hour, which is 560 miles per hour. And then they can carry much heavier loads that way as well. So, fun fact about how technology has changed since the 1950s. Okay, example 5, a power climb. A 50-kilogram marathon runner runs up the stairs to the top of Chicago's Willis Tower, formerly known as the Sears Tower, which is 443 meters tall. And that was formerly the tallest building in the United States, no longer true. But anyway, to lift herself to the top in 15 minutes, what must her average power output be in watts, in kilowatts, and in horsepower? Okay, so you can tell just from the question, we're going to have to do some more unit conversion. Get used to practicing that skill. But anyway, let's take a look at what we're given here in this problem. We know the mass of the runner. We know the height of the tower. So that's the displacement, right? And we know the time that she is doing this run in. Okay, of course, that time is in minutes, which is not a very convenient unit to use. So we'll probably have to convert that. Okay, so based on what we're given, we have two strategies. We could first determine how much work she does and then divide it by the time. Or we can calculate the average upward force she has to exert in that direction and then multiply it by the upward velocity. So let's do it both ways. Okay, first strategy would be finding the work and then dividing it by the time. Okay. So to lift a mass or to lift yourself against gravity requires work that's equal to the weight multiplied by the height, right? That force, the weight, mass times g is the force, multiplied by the height, that's our displacement. So work is force times displacement. So mass is 50 kilograms, g is 9.8 meters per second squared. The height is 443 meters. So that gives us a work of 2.17 times 75 joules. Now we know that that took 15 minutes to do, and there are 60 seconds in 1 minute, so that's 900 total seconds. So that means the average power exerted was that work done divided by how quickly she did that work. So that's 241 watts. To go to kilowatts, remember that's a metric to metric unit conversion. So we just need to remember what that prefix kilo means, which means 1,000. So we're going to take that watts and divide it by 1,000 to get to kilowatts. So that gives us 0.241 kilowatts. And then using that same conversion factor that we did previously, 746 horsepower. That gives us a horsepower of 0.323 horsepower. Okay, so that's one strategy, the first strategy that we could use. Okay, so here I just wrote out for you so you can reference it later on, how we converted between those units. Set it up as fractions so that the units cancel out and you look at what you want. Same thing here, 1 horsepower equals 746 watts. Okay. Strategy 2 was to calculate the average upward force that she's exerting in that direction and then multiply it by the velocity, right? So we want that parallel force, parallel to the direction of motion, which is up in this case, and then multiplied by that velocity. So the force that she's exerting is vertical because she's fighting against gravity. So that's a vertical force. And the average vertical component of the velocity is that change in position over change in time. Right, so she's covering a displacement of 443 meters, again in 900 seconds. So here is our velocity. That parallel force, once again, is fighting against gravity. So that's mass times G. So 50 times 9.8 times that average velocity is once again 241 watts, or 0.241 kilowatts, or 0.323 horsepower. So two different strategies that we used ended up at the same place. Both are equally valid. So this is one of those cases where, depending on what you're given, what you feel comfortable with, what equations you have written down on your equation sheet, that will kind of point you in which direction to go. But also it allows you to check your work if you're unsure that you're correct. Okay, so here's a problem for you guys. An elevator rises at 0.9 meters per second and can lift 1,200 kilograms. What is its power? Okay, if you don't have a calculator, grab your phone, grab a calculator, do mental math if you're very skilled at that. Give this a try and we'll come back and talk about the answer in just a minute. All right, so that might not have been enough time to type all of the numbers in your calculator, but hopefully it was enough time to get your brain thinking through this problem. Let's talk about that. So in this case, we're going to once again use that same equation for power, the parallel force or force in the direction of motion times the speed, because that's what we're given here in this problem. Right, so we're fighting against gravity when we're rising in an elevator. And so that parallel force is mass times G. So the mass is 1,200 kilograms, G is 9.8. The speed of that is 0.9. So that gives us a power of 10,600 watts. Okay, any questions about power before we move into gravitational potential energy?
I'm pretty good.
All right, I'm glad to hear it. Well, let me stop sharing this PowerPoint then, and I will open up the next one. Okie dokie, can we all see potential energy and energy conservation?
Yes.
Yay, good. Okay. Yeah, so far we've just talked about kinetic energy, which is the energy of motion. But there are lots of different kinds of energy that we'll be talking about. Victor, I see you raising your hand.
Quick question with regards to the formulas that you showed us earlier for average power and instantaneous power. These types of formulas, or will they be commonly found within the workbook, for example, that the teacher recommends?
Yeah, they might not be written identically to how I have them written, but the equations should be in there in some form.
Thank you.
Okay. All right, so just a quick revisit the work energy theorem here, because it's an important thing. So we had just talked about it in chapter 6, or the last PowerPoint, that the total amount of work is equal to the change in the kinetic energy. But the total work depends on all of the forces that are involved in the system. So that could be gravity, it could be work done by a spring, it could be work done by something else, for example, friction or air resistance. And so all of those things added together equals our change in kinetic energy. So today we're just going to focus on work done by gravity, and then we'll come back to work done by a spring or work done by other things later, probably tomorrow. So let's figure out work done by gravity. Okay, so remember from gravity, our standard convention is that gravity points down towards the center of the Earth or the planet or this whatever it is that you're standing on. So the force of gravity is equal to mass times G, and G, remember, is that 9.8 meters per second squared. We also should remember from yesterday that work is force times displacement times the angle between those two things. right? So these two equations should look familiar to us so far. Now, if something is falling straight down, as we would kind of expect things to do, the force of gravity is downward, which means displacement is downward. And so the angle between the force and the displacement is 0, which means the cosine of the angle is 1, right? They are in the same direction. The force due to gravity and the displacement, same direction. So all of that force is our parallel force, or acting in the direction of the motion. So that means that we can kind of ignore that cosine theta portion of our equation. Not really ignore it, but just remember that it equals 1, right? And anything times 1 is just the same thing. So the work done by gravity, we can just kind of write as force times displacement times 1, right? And that force is mass times g, 9.8, times our displacement. If we are lifting something straight up, well, now the force of gravity is down, but the displacement is up. And so those two are directly opposite each other, which means they're at an angle of 180 degrees, and the cosine of 180 degrees is -1. So if we're lifting something straight up, now the work done by gravity is negative force times displacement, or force times displacement times -1, right? So it's just the opposite of that equation from before. So that means that as an object is falling down, the work due to gravity is positive, right? Gravity is assisting it in its fall. And as we're lifting an object up, the work due to gravity is negative. Gravity is kind of taking energy out of that system, right? As you're trying to lift it up. So this is often kind of inconvenient because we have to remember like which direction we're talking about and treat it a little bit differently each time. So we want to try to look at gravity in a different way, and that's using gravitational potential energy. So gravitational potential energy is the energy that an object has due to its position. So it's relative to a reference point, right? When we're thinking about position, it's always relative to some reference point. Whether that's relative to the starting line in a race, or relative to the floor or the surface of the earth, or some point, the top of the building. We always need to have a reference point in mind when we're doing gravitational potential energy. So if the object is away from that reference point, let's say the reference point is the floor. Okay. If the object is above the reference point, now it has the potential to fall because of gravity. That means it has gravitational potential energy, right? Potential to fall because of gravity, gravitational potential energy. Right, so if something is on the ground, it has no potential to fall anywhere, so its gravitational potential energy would be 0. There's no potential to fall. But if we lift it up a little, it has the potential to fall a little. If we lift it up a lot, it has the potential to fall down a lot. So that distance away from that reference point is very important. Okay, so again, just kind of like with kinetic energy, there are lots of different ways you might see it written depending on the professor and the textbook. You may see it as GPE for gravitational potential energy. You might see it as just PE for potential energy, although that one is probably the most uncommon, simply because there are other forms of potential energy as well that are not due to gravity. Most professors like to use U for gravitational potential energy, capital U, and some of them will specify it as U sub G. I don't know why it's U, but it is. The units of it is joules again, because it's an energy. And the equation of this is mass times G times the height above our reference point, or distance from the reference point. So you could see it written as MGH or MGY or MGD, right? Why? Simply because we're only concerned with the vertical component of this, not really horizontal because gravity doesn't pull things horizontally, it pulls things vertically. And then that D is just, again, displacement like we had seen before. You may also see it written as the change in potential energy is mass times G times the change in its height. Okay. Again, it all depends on the textbook that you use, the professor that you have. You might see it written multiple different ways throughout your study of physics. Okay, but again, these like H, Y, and D are all relative to some reference points. Okay, so you can choose that zero height or that reference point to be wherever you want, just like we did for projectile motion, for example. The difference in the height will not change. You'll still have the same distance, regardless of what your 0 point is. Just make it wherever is most convenient, and then keep it consistent throughout the whole problem. So that means potential energy is relative, right? There's no absolute amount of it, just more or less than you would have somewhere else. Okay, so here's an example. If we want to determine the change in potential energy of a 2 kilogram book as it falls 1 meter from the top of the table to the ground, let's take the ground as our reference point for this example. Okay. So to determine the change in potential energy, we have the mass. We're assuming we're on Earth, so we know that gravity is 9.8. And we know the change in its height, or that displacement that it falls, is 1 meter. So here's our picture, right? We have a book sitting on the edge of the table. It's going to be falling down to the ground. The ground is our reference point of 0 meters, which means that if it's falling a distance of 1 meter, it's at an initial height of 1 meter. So the change in potential energy is the final potential energy minus the initial potential energy. We are going to calculate it using mgy, just because we have our positions labeled as y equals something. So at the end of its journey, it is at a height of 0 meters because it is ending up on the floor, which is our reference point of 0. Right, so we have the mass times g times a height of 0 minus, and here's our initial potential energy chunk, mass times g times the initial height of 1 meter. So that means we went through a change in potential energy of negative 19.6 joules. Okay, fairly straightforward to calculate. Now, if we want to take the top of the table as our reference point, not too much changes, right? We're still falling a distance of 1 meter. It's just that now the floor being below our reference point, that makes it have a height of negative 1 meter because it's below that reference point. So same setup, right? We're still trying to determine the change in potential energy. So it's final minus initial. It's just that now our final height is negative 1 meters. Right, relative to that reference point of the top of the table, the final height is negative 1 meters. And its initial height is 0 meters. So we still end up with a change in potential energy of negative 19.6 joules. It does not matter where you put your reference point as long as you keep it consistent. Okay, so you got the same answer either way. Okay. Gravitational potential energy versus work. So as an object falls down, that gravitational potential energy becomes less, right? Because it has less potential to fall, the more it falls. Right? The height above our reference point is getting smaller and smaller. So that gravitational potential energy is becoming less, which means the change in gravitational potential energy is negative. Now, vice versa, when the object is being lifted up, now it has more and more and more and more potential to fall down. So that potential energy becomes more, or that change in potential energy is positive. So that means when an object is falling down, the work done by gravity is positive. As an object is lifted up, the work done by gravity is negative. Right? Where in the case where it's falling down, gravity is assisting that fall. So it's positive work. When we're lifting it up, even though the potential energy is becoming more, that means we're fighting against gravity. And so the work done by gravity is negative. It's not assisting the fall, it's fighting against the fall. So that means that our change in gravitational potential energy equals the negative of the work done by gravity. That is an important thing to notice. Okay, so this negative sign is essential. Do not forget it. You will lose points on a quiz or test. Because, yeah, like I said, they don't have the same effect as each other. Okay. So change in potential energy equals negative work done by gravity. When gravity does the work. So previously we saw it written as this on the last slide. We can also move the negative over to the other side and write it in this form. They mean the same thing. So we know from before that the total work done is equal to the change in kinetic energy. And we said that the total work done can depend on lots of different types of work. So work done by gravity plus the work done by a spring plus the work done by other things equals the change in kinetic energy. Okay, we're not dealing with springs yet. We'll get back to that later. Okay, so here's our work done by gravity, and it is negative potential energy. So plug that in there. So our negative change in gravitational potential energy plus work done by other things such as friction equals the change in kinetic energy. Okay, so if we want to rearrange just a little bit more, work done by other things equals the change in kinetic energy plus the change in potential energy. And we usually just call that the change in total energy, or delta E. Okay, so like I said, the work done by other things could be friction. It could be any other external force too that we haven't mentioned yet. But those are things to consider as well. Okay. So if the total work done equals the change in the kinetic energy, but also the total work done equals the work due to gravity, which is negative change in potential energy, then we can combine those equations and rewrite it as such. So the change in kinetic energy, K2 minus K1, equals the negative change in potential energy, U1 minus U2. Okay, so notice that these subscripts are switched, right? So kinetic energy here is final minus initial, that's the change in kinetic energy. But here they're flipped because of that negative sign. Boop, 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 right there. Okay, so that means we can also rearrange this equation a little bit further and get our initial kinetic energy plus initial potential energy equals final kinetic energy plus final potential energy. That is a very important and powerful way to rewrite this equation. So our initial energy equals our final energy. And that's where this idea of conservation of energy comes into play. Energy is not being created or destroyed. It is conserved, it is saved throughout the entire process. Whether it's moving or falling or whatever the object is doing, the total amount of energy stays the same. So this initial energy equals the final energy.
Could it be like it's being changed?
Yes, it can change from one form to another form of energy. Absolutely, it can. But it won't just like disappear into the void. Okay, so this idea is called total mechanical energy. When we think about adding together kinetic energy or energy of motion plus potential energy or energy due to its location, the sum of those two things is called the total mechanical energy. And usually we just give that the symbol E for energy. Okay. So E equals K plus U, or kinetic plus potential, and that is a constant, right? Conservation of energy. The total amount of energy stays the same the whole time, even if it changes from one form to another. The total amount is a constant. Right, so something that always has the same value is called a conserved quantity. So this is conservation of mechanical energy. So let's think about this idea of throwing a ball into the air, right? That's something that you have probably done before in your life, just to guess. So on the way up, you'll notice that the ball, which is initially traveling pretty fast when it leaves your hand, slows down. And then as it falls back down, it speeds up, right? We talked about that in projectile motion as well. So on the way up, the speed of the ball is decreasing. But we also know then if the speed is decreasing, that means the kinetic energy is decreasing, because kinetic energy depends on the mass and the speed. Now the mass of the ball is not changing, hopefully, but the speed is, right? So if the speed is decreasing, that means kinetic energy is decreasing. But again, that kinetic energy isn't just disappearing into the void, it's turning into something else. Because as that ball is traveling up into the air, it's moving higher above our reference point. So that means the potential energy is increasing, right? The higher you get above your reference point, the more potential it has to fall because of gravity. So that kinetic energy that we had at the beginning is turning into potential energy, gravitational potential energy, as it's going up. Okay, so our change in kinetic energy is negative because it's losing that kinetic energy, but our change in potential energy is positive because that kinetic energy is turning into potential energy. On the way back down, the opposite happens, right? Initially, it's starting slowly and then it speeds up the more it falls. So initially, it has zero kinetic energy, but by the time it reaches your hand again, when you catch it, it's moving pretty fast. So it has a larger kinetic energy. Although the closer it gets to your hand, the lower its potential energy gets because it has a lower potential to fall the closer it gets to your reference point, being your hand or the ground. Right, so that potential energy is now turning into kinetic energy. But at every point in this ball's path, the total mechanical energy is the same, right? It's just changing from one form to another form of energy. Okay, so here we have an example, throwing a baseball. You throw a 0.145 kilogram baseball straight up in the air, giving it an initial upward velocity with a magnitude of 20 meters per second. We can find how high it goes, ignoring air resistance. Right, so we haven't done like work due to friction, air resistance. We're not concerned with that for this example. So here's our little picture, right? Here's the ball, we're throwing it up. Initially, we're throwing it upward. We're not throwing it up. Okay, anyway, it has an initial speed of 20 meters per second upward. Here's the mass. And at the top of its trajectory, right before it changes direction, the speed of the ball is momentarily zero, right? We talked about that in projectile motion. So here when it leaves our hand, V1 is 20, V2 at the top of its trajectory is 0. Okay, over here, these are energy diagrams. So these bars are showing you what the energy is doing at each location. Just kind of like a visual representation of the energy. right? So initially, all of the energy of the ball is kinetic energy, right? Because it has not really left our reference point yet of our hand. So it doesn't really have any potential to fall yet. So its gravitational potential energy is 0. All of its energy is kinetic due to the fact that it is moving quickly. And remember, E is our total amount of energy. So this E bar stays the same the whole time. But at the top, when it is momentarily a speed of 0, that means it has 0 kinetic energy. And all of that energy has transferred from kinetic energy into gravitational potential energy. Okay, so point 1 is at our hand, point 2 is at the top of its trajectory. At point 1, its gravitational potential energy is 0 because it is still at that reference height of 0. At point 2, the kinetic energy is 0 because it is no longer moving. The speed of the ball at the peak is 0. So if we think about our conservation of energy equation here, initial energy equals final energy, we can simplify some of these terms, right? So this initial potential energy is 0, and this final kinetic energy is 0. Okay, so kinetic energy, 1/2 mv squared. Potential energy, mgy or mgh. You'll notice that there is a mass in both of those terms. And so we can cancel it out. We don't even need to know the mass of the ball at all. So if we want to find that final height, then we can simplify this equation to solve for that final height. We just divide both sides by g. So 1/2 m canceled out, right? So 1/2 v1 squared divided by g. That initial velocity is 20 meters per second. We square that. And then we divide by 2 and divide by g. So our final height is 20.4 meters. Okay, so I'm going to stop here because it's 4:29, and we'll pick up here tomorrow learning about when forces other than gravity do work. So that W other term is what we'll be talking about tomorrow. But do you guys have any questions about this example or gravitational potential energy or power so far?
Can you go over example 1 again?
Maybe. This one?
Oh, no, like the slide before example 2.
Oh.
My bad.
No worries. You let me know when I get there. This one?
Yeah, that one.
Okay, so which part did you want me to go over again?
That very last part, like when you throw a ball up into the air.
Okay, yeah. So when we throw the ball into the air, like we just did in example 2, so as the ball is traveling up, and I mean, you can do this with any object in your home too, probably not your computer, don't throw your computer, but any other random small object, you'll notice that as you throw it up into the air, it's traveling pretty quickly at first, and then the speed decreases as it reaches its peak. So since the speed is decreasing, that means the kinetic energy is decreasing, right? Because kinetic energy depends on mass and speed. So if speed is dropping off, that means kinetic energy is decreasing. But since the ball is now going higher and higher above your reference point, that means that it has more and more potential to fall to the ground, more chance to fall to the ground. And so it has more gravitational potential energy. So that kinetic energy is decreasing. At the same time, the potential energy is increasing. And not only at the same time, but by the same amount, right? All of that kinetic energy transforms into potential energy so that we can keep our total amount of energy constant. Right? Conservation of energy tells us that the total amount of energy has to be the same at every point in the scenario, no matter what is happening. So on the way up, the speed decreases, that kinetic energy turns into potential energy. On the way back down, the opposite thing happens, right? It starts off really high above our reference point, but as it's falling down, it's getting lower and lower and lower. So that distance between the ball and the reference point gets smaller and smaller, which means our potential energy is decreasing. But as it's falling down, it's moving faster and faster and faster. So that potential energy is now turning into kinetic energy. Again, the total amount stays the same. So the total mechanical energy is the same at each point, regardless of how much of it is kinetic or potential, because the total amount of energy is the sum of those two things together. Does that make sense?
Yes, it does.
Perfect. Okay. Any other questions?
Um, can you go over example 2? I was away from my phone.
Yeah. Let me go ahead and stop the recording then, and then I can go through it with you without the recording. Sound good?
Okay. Yes.
Okay, cool. Well then, I hope you guys have a great rest of your day, and I'll see you tomorrow. Bye.